months. They are now unplugged as we are making space for a new installation, which I'll mention a little later. We have some disk, some tape, all Sun product. We have a Sun rack with 21 nodes with dual-core AMD chips, and we're also installing some, I believe they're called Dorado boxes, which I forget the actual Sun product name right at the moment. And of course the 78. We have, out of the 78, 68 have 32 gigabytes of RAM, and 10 have 64 gigabytes of RAM as we go. And actually, Mark Hamilton mentioned what we are purchasing, of course, and that's the M9000s with the new chip, etc. And those are starting to arrive, and we've got some extra people in the computer room right now running around getting the power ready and all sorts of nice things happening there. Well, what was the rationale for going with the 5140s? And that basically you have to think about what's happening in the world, and what was happening has been going on. If you've come to the Sun events for a number of years, you've been well briefed by Mark Tremblay and others as to the rationale for going to chip multi-threading. And it was kind of interesting to see a little article in the Register which had a link to a quote of Bill Gates and the CTO of Intel. And Bill was saying, why are you changing this? Why can't you just keep bumping up the speed? And the CTO for Intel saying, Bill, that's just the way it is. So that was kind of an interesting thing to see happening. Even, you know, I have researchers who are basically saying the same thing to me. Why are you doing this? And it's kind of interesting. So you just go through a very simple explanation. Chip temperatures rising, physics, etc. Latencies, i.e. the development of CPU speeds and feeds. The feeds are not quite keeping up there. And in particular, I stole a portion of an old Sun slide that I had lying around from one of the presentations many years ago, which without any numbers or years, you can basically see what was happening. And that is basically that you're getting a CPU speed up in terms of the appetite, and you're waiting on memory quite a bit. So without going into the CMT sort of thing, I took this from the latest technical document that came out when the 5140s came out, which showed the what's happening in these systems in the T2 Plus, and how, if you think about the Niagara 1, you had the 4 threads per cycle, basically, with the overlap, and here you have 8 happening. And it's kind of interesting because we were starting to do some benchmarks, and we were wondering how things were working and what was going on. We got the technical documents as to how this was being done on chip, and we started to understand a little bit better as to how things are actually running. So this is kind of interesting. But Ruud showed some technical schematics, and I'm not going to get into that, but I'll just give a description of what's there. The TPP that you'd have for your box, essentially, it's a 1U box. It has 19.2 gigaflops max, okay, if you're thinking of theoretical peak performance. But when you're also looking at this, this is only the floating point limitation that you're talking about, okay? So when you're looking at this, what other types of instructions would be carried out? Okay, what other types of things would be happening that you can be doing, other things going on? Because we're the interface with the users. We're looking at our user base. We're looking at some other users coming on board other than the physics, chemistry, and engineers that we've had typically chewing up a lot of our cycles. We have some other people coming on board, and they actually have a number of applications that, yes, there's some floating point, but there's also a lot of other work that they need to get done. And the real estate in a 25K or an M9000 is a relatively expensive piece of real estate. So you'd want to be able to have the resources there for other people. So we started asking these questions, and when we saw the Niagara 2 Plus, and in particular when we saw the numbers that were being presented from the folks in Aachen who had done some work on benchmarking the beta systems for the single socket, we were saying, you know, this is an interesting thing to look at and to see how we can deliver certain resources to various researchers. So we've been having meetings with our user groups, basically saying, how do you do your calculations? Is there some way you can take advantage of this? I mean, obviously there are going to be some users who will not be able to take advantage of this, but we wanted to make sure that we could get a sort of a basket of researchers who may be able to take advantage of the types of machines that are coming, and also to try and figure out which types of machines would be most advantageous given the stage at which our researchers are at in terms of the programming. So I'll mention that famous line that's appearing more and more in the high-performance computing sort of press, and that's the software crisis. That's the US sort of stuff that's been talking about, and that is being able to take advantage of the hardware, okay? There's an awful lot of people not even really thinking about it yet. So these are some of the questions that we asked our users. And so we started looking at some of the types of things that people typically do. And as well, we're trying to get the users not just to think only of a single process, because that's the way they've been sort of thinking. And with the Microsoft and Intel sort of duopoly, I guess that's been going on for years, a lot of people just automatically think that you're going to have a faster cycle speed to get your computation done faster, okay? Get me the chip that runs fastest. And in fact, what you see right here is that if you're looking at a relative performance, say, of an UltraSPARC 4 Plus box, you see some relative scaling up to 16 threads or processes. And then you go over to Victoria Falls, and this is just a fast Fourier transform. You can see that, well, it takes a while to get there, but it gets there. And this is in a 1U box. So if you have something that scales, you can actually get equivalent performance, because a lot of the stuff that would keep the UltraSPARC 4 Plus job from scaling very well past a certain limit would actually be hidden in the Victoria Falls type system. So you get actually the same performance, and of course 32 processes on UltraSPARC 4 Plus is a lot of real estate. That's a couple of boards, which are not cheap. And then you look at the, what you're looking at is a 1U box that comes in at I'd say about $20,000 after your discounts and so on. So it's quite a big difference. This is a bit of a chemistry code that one of our user groups basically took, and they said, okay, we have two ways of doing something. Let's just test out this box and see what's happening. So this is just basically looking at how things scale. Again, using threads. Threads are cheap versus hardware. Okay, so threads are cheap. So that's the idea that we were trying to get across. And they were just looking at things, seeing how it was scaling, and not bad. But then you go into away from more MPI to a less memory and less MPI type of thing. You see much better scaling. So this is the type of stuff we're doing. In this particular case, you can see, I thought I'd just point this out in real numbers, 32 threads on what was codenamed the Miranda box versus 4 processors on a Sunfire 25K. Okay? You can go through some of these. You go to the other model, you see 32 threads, then you see 8 processors on the 25K or 4 processors on the 25K. So for some things, you're actually seeing pretty good results. And I'm just going to, this is actually a cross between chemistry and physics code. This is looking at a parity function calculation. It's just seeing how you scale. You see over here you have MPI processes, and over here you have threads per process. Okay, and just looking at the various things. If somebody would like to look at these a little later in terms of the numbers, I have them with me. But you can just see how things scale and what you can get within the box. Okay. There are some places where you run into what I call the real user attitude. If you have not educated people, we had some folks who have some CFD code. They went and did some benchmarks and sent us these results and said, these boxes are absolutely useless. Okay, absolutely useless. And we sort of said, oh. So when I was going around to some other groups, I said, I'm not sure if I should show these numbers to people or not, but I think it's really a good indication of how people view computing and what's going to come out of something and what effort has to be put in. So without making any changes, folks didn't make any changes in their codes, by the way, when we were doing this. This was just purely just taking things. In some cases, people took things that had been compiled in UltraSPARC 3, okay, and ran it, so there's no real thing. And in this particular case, we did get them to compile it using FAST as the only option of the compiler that we used. So basically, you can see CPUs or threads. And as you can see over here in the first part, okay, so the first part is a larger problem than the second part down below. And you can see that 120 CPUs, CPU cores, on a 25K took 5 seconds. Okay, okay, we don't quite get there on the 5140s, but you're still doing not too bad considering the real estate that you're not using. This is all being done within a box. Okay, so you've got pretty good comparison. You go down below, and again, this did not scale very well on the 25K, but you can see that we kept getting gains as we added more threads on the Miranda box. So it was kind of an interesting thing. We actually, this was sent to us with the quote that I just gave you by the graduate student. So we actually, in the end, decided to have a word with the prof and the grad student and just sort of go over it with them and explain what was going through. They're still not happy because they're still equating getting work done with a faster processor. That's the way it is right now. And in fact, many of the other codes that they in particular work with will probably not scale very well for them to get their jobs done, okay? One thing I should say is that we have these things connected right now with a gigabit Ethernet, and once you go off box, performance degrades very, very badly, okay, for a lot of these codes. So we are looking at a possible interconnect, either 10 gig E or maybe even using a nano switch if it's possible to do so, but we're taking that into consideration. The other side of the equation is that here we are, we're going into this threaded world, and in fact we have software vendors who are not very threaded. They are very much not quite ready for this world. Reason why is that everything's done by process. And on a Miranda box, for example, every process is considered a CPU. And of course, you go to the software vendors, every CPU is basically a license. So all of a sudden, if you're going to a slower process or sets of slower threads, you're going to have to buy more licenses at the moment. Okay, so some people are working on that. And certainly if you're looking at some other things, there's more than just your own community that will have to change over the next few years as we move into this threaded world. And this is not just a Sun hardware problem. This is actually the community problem that we're going to be faced with. Okay, so I just thought I'd put you there. I quoted the prof who actually we went and talked to. The student had said what I mentioned. The prof just said, I just want my code to run faster. I don't want to do any work. Okay, you guys are supposed to bring me stuff that makes it run faster. This is the difficult part. Software vendors are not seeing the need, and so we have to start thinking about what's going on. And that brings in other issues as well, also from the administrative side of running computer clusters and centers, where you have a mixed bag, where you may have different ways of allocating resources. And in Canada right now, we're doing a number of things, which means that you have issues with researchers moving from center to center, where they may be allocated resources. We're trying to put a national allocation process in place. And so we're starting to think about how do you consider, for example, a CPU hour. What's a CPU hour if you're using multiple threads versus using one very fast CPU? So it's a comparison you have to go through. What's a slot in the queue? And what's a process or a job worth in terms of the system's dependence? Just wanted to put this up here. What's the cost of a thread or a process? So if you have a board with fast threads costing you $400,000 list price for 8 threads, that's $50,000 per thread. And then you go to T5140, and that particular code runs very nicely and scales very nicely, then all of a sudden you're looking at a possible cost of $310 per thread. And so you only need 4 of them to get the same performance. So it really does give you an opportunity to say to the researcher, you maybe not need to be over here. You maybe need to be over here. If they need large memory, maybe the 5140 is not for them. They'll have to move them to the next iteration. But the other side of it is that a lot of people are getting very sensitive in the university environment in Canada about power. And the ability to get work done for a specific amount of power is something that's coming into our language when we start talking to people. It's just the start. But that's why we decided to go with this particular cluster, because this is really massive CMT now. We can educate people, and when we do get the massively threaded, faster processors later, and with the software availability, we'll have people educated. And one of the things, I'll just go down here, as I mentioned, Mark mentioned our new systems coming in, and we hope to have those available to the users in July. The biggest thing is lots of help for users as we move into the CMT environment. This is going to be a real education process. There's not a lot of software out there for them. Some of the tools even that Sun has, and I'll be very blunt, it's nice that there are some cool tools, but unfortunately you need to be root to use some of those cool tools, and we don't give our users root privilege, okay? It's a little thing that we do. And lastly, as of this past week, we've committed to hosting the next Canadian High Performance Computing Symposium. It will be held in Kingston, Ontario, starting June 14th to 17th. And I'm just going to mention that I'd advise you not to travel if the 13th falls on a Friday. I had that experience this week. But unfortunately, the 13th falls on a Saturday, so you'll be okay if you want to come and get there on a Saturday, okay? More details will be posted as we go along, so that's just the announcement for it. And thank you for your time, and any questions, I'd be quite willing.
First of all, thank you very much, Ken. Quite amazing how amazingly well he's doing, given that he arrived here this morning after a dreadful long trip out of Canada. So I'm impressed by just by that. Any questions for Ken? I'm sure you have them. Maybe you want to share them over dinner or the drinks. Quite breakthrough work they're doing, I think. So thanks again. Yeah, there's a question. Dieter?
So maybe I missed this in your talk, but talking about CFD codes on the system, how are you looking to cluster these nodes? Or are you looking at clustering these nodes?
Yes, we are. And that's, I mentioned the interconnect. Right now it's gigabit Ethernet, and performance just falls way off once you get outside the box. So if you're on the box with less than 128 threads or less, you're fine. You get fairly good scaling on a lot of codes. But moving off the box, the degradation in performance is really bad, okay, right now with the gigabit. Now, there may be some stuff that we have to do. I will say that the other side of it is that we just added this into our SAN, and one of the benchmarks that we decided to run, not the benchmarks, one of the things we decided to do was to try and experiment a little bit on a throughput experiment, which was to take the Gaussian test suite and those jobs that don't require large memory and just throw them in different ways at the system. Our file system didn't like it. Okay, became very unbalanced and exposed a problem in hardware. So we actually crashed our file system. Okay, it was not a nice thing, but it just basically had thousands of processors going through essentially 2 NIC cards, and essentially the other systems were also very busy. So the contention was just too much and too many things saying, I'm waiting, and finally our file system decided this is enough. So we've had a lot of discussions with some Sun engineers about all of this. So. And one of the things we'll be doing actually over the next couple of weeks is trying to ensure that we balance the file systems a little better as we bring the M9000s on board. Because again, we're going to have 2,000 CPU cores, and that's another 4,000 or so threads. So that'll add a little complexity coming from another different cluster. So.
Right. Thank you, Ken. No more pressing questions. Then I have a few messages, and then we're done. First of all, dinner starts at 6, not at 7.